Alright, so in this example we have a solenoid with a specific length and a specific radius and a certain number of turns. And it's passed through the center of a coil that has a certain radius and a certain number of turns. Alright, so at one particular moment there we have the current in the solenoid, implying that the current in the solenoid is changing. And that the current is increasing at a specific rate. So we want to know what the magnetic flux of the coil is, not the solenoid, the coil. What is the mutual inductance, and what is the induced EMF in the coil? So the first thing we need to do is pull out our magnetic flux example. And remember that magnetic flux is equal to the magnetic field times the area. And now we have to be careful, and I mentioned this in the video as well. We want to know what the magnetic flux of the coil is, but remember that flux is being generated by the solenoid, not from the coil. The solenoid is the source of the external field that is going through the coil. So when we do this, we're plugging in the magnetic field equation for a solenoid that we derived using Ampere's law earlier in the semester. So then I can plug in the magnetic constant, the number of turns for the solenoid, divided by the length of the solenoid, and the current at that particular moment. And then I almost forgot the area and kind of squished it in here using pi r squared because it is a solenoid which has a cross-sectional area of a circle. And then we can calculate that magnetic flux. Remember that the units for magnetic flux are Webers. We then want to know what the mutual inductance is. And we have two equations with mutual inductance. One of them doesn't work because we don't know what the induced EMF is. However, we do have this other equation that I use as part of the definition of mutual inductance. And so we know the number of turns through the coil, and then we have the magnetic flux we found in part A. So remember, there's two ends here, one that's for the one experiencing the induced EMF, or one that's actually exerting the induced EMF. So there's actually two ends, one on the outside here and then one that was actually inside of the magnetic flux equation. We're solving for mutual inductance, and then once again we know that current at that particular moment. So then we can plug in, remember the units for mutual inductance are henries. And the last thing we want to do is find the induced EMF, so we can pull out our other equation. Once again, just like with Faraday's law in the previous chapter, we tend to drop the minus sign. So we know what the mutual inductance is, and you're told the rate of change of current with time in the problem up here, so you can find your induced EMF.